We're going to look at some graphs of derivatives and try to get a deeper understanding of what they actually are. We have a cubic function, and I went ahead and graphed it. I did this on Desmos, and I printed it out and traced it so you can see it a little better. But I'm going to go ahead and find the derivative of this function. And I differentiated, and we got a quadratic equation here, which means we're going to get a parabola when we graph it. So now I'm going to graph the first derivative. And I chose this notation because it's much easier to work with than the other notation, which once we're learning about second derivatives, you'll see why this is much easier to use. But that's beyond the scope of this video. So this is the graph of the quadratic equation, which was the derivative of the yellow equation, the cubic function, that I showed you the equation of earlier. And what we're going to do at this point is look at our two stationary points. Now the stationary points are the local maximum and local minimum. So we have a local maximum right here. We're going to call this point P, and I just happen to know for a fact because I looked at Desmos that this is occurring at -1 1/3, -1 1/3, so -1.3, and 1.185, which we're going to call 1.2. We're going to round, okay? And our local minimum is occurring here at the origin, and we're going to call it Q. And that is at the origin, so it's at 0, 0. Now the parabola, remember, think back please, and remember that the solution of a derivative, when you put in a given x value, is the slope or gradient of the tangent line at the point where that x value is. Now that was a mouthful, so I want you just to, if you didn't get all that, it's okay. That's why I'm showing you this visually. So if we think about this, and let's go ahead and use the stationary points. -1.3 and 1.2, or -1 1/3 to be more accurate. And we're going to determine where the graph of the derivative is, where the y value is, where the output is. So where is the output? Well, let's think about this. At the stationary points, what is the gradient of the tangent line at the stationary point? Well, I already made a video about this and you saw it. It's 0 because it's a horizontal line, because we are at the peak, we're at the local maximum, so it's going to be 0. Well, look at this. What's the y value then at -1.3 directly below this? What's the y value? Well, it's 0, so that's the gradient. So we found the derivative, the output, when we put -1.3 into the equation. You can do it algebraically as well, and it should come out to be 0. I'm going to do it algebraically a little later. Right now, I want you just to think about the graphs. Let's look at this resting point at 0, 0. Okay, well the gradient is 0, or stationary point, I called it a resting point. I'm trying to use the correct terminology. Okay, so we have a horizontal line here at the stationary point. And what about the parabola? What's it doing? What is its y value when x is 0? Well, it's 0. It's on the x-axis. We're going to use one more point. Let's go ahead and use point R, which is at -2, 0. Let's think about this. Let's follow this up to our parabola, which is the graph of the derivative of our cubic function. And we can follow this over, and it looks like, according to this, that the gradient is going to be right around 4. Let's come back here. Well, it sure is a steep positive, so it looks like the gradient is 4. 4-ish at least. And let's get a ruler, and I'm going to draw it, and we're going to see what happens with this line. The tangent line, I should say. So I went ahead and drew a tangent, and look at that. Now remember, 2 of these boxes is 1 unit long, so for example, that's 2, and that's -2, and that's 4 boxes. Okay, so look, it looks to me like if we touch at point R, the gradient is 4. And just to ensure it, I went ahead and did it algebraically, and look at that. We found out that the gradient of the tangent line is indeed 4. I want to test one more, but this graph is getting a little bit busy, so I want to use a clean graph. And I want to test one more point. So I want to look at 3, 3, because as you can see, and I double checked, I ran it through the equation, and if I put in 3 for the y value and put it in for x value, both sides are equal. So that means that this cubic function crosses through 3, 3, which is right here, and I don't care, we're going to call it z. And this is 3, 3. So let's run it through the equation. But prior to that, I want to look at this graphically. So what do you think this parabola is doing at 3? It's getting steeper and steeper. So it's going to indicate what our gradient is. So when x is 3, well, it's been cut out. So we're going to do it all algebraically. So here we go. Whoops. Here we go. Our equation is 3x squared plus 4x. 3x squared plus 4x. We're going to put in 3, so we've got 927 plus 12. And we've got 39. That's a very steep slope. So let's look at what's happening at 3, 3. And you can see it's almost a vertical line. So that means the tangent line should be 39. The gradient of the tangent line, I should say. I'm going to try to draw this. I don't have a ruler, I'm at home. But you can see that this tangent line has a very steep slope. It's going to be 39. So I hope this helps your understanding of derivatives and thinking about it graphically.